Have you ever stopped to think about what a rolling bicycle wheel, a spinning top, and a pirouetting ice skater all have in common? Well, they all play by the same beautiful and surprisingly simple set of rules, the physics of rotation. These rules govern pretty much everything that spins in our universe. Okay, let's dive right in.
So here's the big puzzle we're going to solve. You've seen this, right? A diver flipping through the air or a figure skater in a spin. They can dramatically speed up their rotation, seemingly out of thin air, just by changing their posture. How is that even possible? It feels like it breaks the rules, doesn't it?
I mean, an athlete like this can literally triple her rotation speed with no outside help. It seems to defy the laws of motion. It looks like magic, but I promise you it's not. It's one of the most elegant principles in all of physics, and by the end of this, you'll understand exactly how it works.
First things first, let's break down the basics of just rolling and rotating. To solve our main puzzle, we've got to start with something familiar, a simple rolling wheel.
The key to understanding a rolling wheel is to see that it's actually two motions combined. First, you've got translation, which is just a fancy way of saying the whole wheel is moving forward. At the same time, you have rotation, the wheel spinning around its center. Rolling is just both of those things happening at once.
Let's break that down visually. Pure rotation is what you'd see if the wheel was, say, lifted off the ground. Every point on the rim is just moving in a perfect circle. Pure translation is like the wheel is on a super slippery patch of ice, sliding forward without spinning at all. Every part of it moves forward at the exact same speed. Rolling is just the sum of those two motions.
And this is where it gets kind of mind-bending. When you combine rotation and translation, the very top of the wheel is moving forward and spinning forward, so its speed is actually double the speed of the bike itself. But at the very bottom, the part touching the road is spinning backward at the same speed the bike is moving forward. The two cancel out perfectly, and for a split second, that point on the wheel is completely still. You can even see it in the blurred spokes here, clear at the bottom and a total blur at the top.
Okay, now for the key concept that's going to solve our mystery, angular momentum. You can think of it as the spinning equivalent of the regular momentum you'd find in, a thrown ball or a moving car.
In simple terms, angular momentum is the quantity of spin an object has. Once something is spinning, it really wants to keep spinning. Angular momentum, which we represent with the letter L, is just the physical quantity that measures this tendency.
And look how neatly rotational motion mirrors linear motion. Linear momentum is just mass times velocity. Well, angular momentum is its rotational twin, rotational inertia times angular velocity. The most important new term for us here is that first one, rotational inertia.
So this is the crucial point right here. Rotational inertia I isn't just about mass. It's about how that mass is distributed. An object with its mass spread way out from the center of rotation has a high rotational inertia. It's really hard to spin. But an object with the same exact mass concentrated near the center has a low rotational inertia, and it's way easier to spin. This is the key.
All right, we now have all the pieces of the puzzle. Let's put them together with the most important rule in the entire world of spin. This is the law that's going to unlock the diver's magic.
This law is called the conservation of angular momentum, and it's a fundamental, unbreakable rule of our universe. It states that if there's no external twisting force, what physicists call a torque, acting on a spinning system, its total quantity of spin cannot change, ever. It is conserved.
Here it is, stated a bit more formally. But that last part is the kicker, no matter what changes take place within the system. A diver in midair has no external torques acting on her. So whatever quantity of spin she starts with, she is stuck with that exact amount until she hits the water.
So here's the idea as a simple balancing act. The total angular momentum, L, is the product of rotational inertia I and angular speed, omega. Since L has to stay constant, you can think of it like a seesaw. If you decrease the rotational inertia on one side, the speed on the other side must shoot up to keep things perfectly balanced.
All right, it's time. Let's take this unbreakable rule and apply it back to our diver and our figure skater. Let's see how the magic really works.
This classic demonstration shows it perfectly. A student sits on a stool that can spin freely. We give him a little spin while he holds weights with his arms stretched way out. He's spinning, but not very fast. At this point, his angular momentum is now fixed. It can't change.
With his arms out, the mass is spread wide, giving him a high rotational inertia and a slow spin. But then he pulls his arms in. He concentrates all that mass near the center, drastically lowering his rotational inertia. And because his total angular momentum cannot change, as his inertia I plummets, his angular speed omega must skyrocket to compensate. And that is exactly what our diver is doing. She leaves the board with her body extended, that's high rotational inertia, so it's a slow spin. In midair, she pulls into a super tight tuck, bringing all her mass close to her center of rotation. Her rotational inertia drops, and to conserve angular momentum, her body just whips around at an incredible speed.
So you see, no new energy or spin is being created. She has the same quantity of spin throughout the entire dive. All she's doing is changing how that spin is expressed. She's trading a large, slow rotation for a small, fast one. It is a beautiful example of physics in action.
Before we finish up, let's look at one last, almost gravity-defying consequence of this powerful law.
Finally, take a look at this gyroscope. If it's not spinning, it just falls over, exactly like you'd expect. But when you get it spinning incredibly fast, something amazing happens. It seems to defy gravity. It doesn't fall. Instead, it just hangs there in the air, slowly tracing a circle. This weird wobbling motion is called precession.
So why does it do that? Well, the fast spin gives it a very large and stable angular momentum. Gravity is still trying to pull it down, of course, creating a torque that wants to make it fall. But because that spin is so powerful, the torque just can't topple it over. Instead, all it can do is nudge the direction of the spin, pushing it sideways. This constant sideways nudge is what creates that slow, wobbling precession.
So, from a diver's tuck to a spinning top, the conservation of angular momentum is a powerful, universal rule. It's what helps keep planets in stable orbits and what governs the shape of entire spinning galaxies. So the next time you see something spin, think about its hidden quantity of motion, held perfectly in balance. What else in the universe might it be responsible for?